We're talking about gravitational field intensity. Gravitational field intensity, if you remember from yesterday, or the last lesson, we talked about Newton's law, Newton's universal law of gravitation. And we said it was this Fg equals g m1 m2 over d squared. And you might notice that this stuff right here, as long as we're on Earth, that stuff is going to be constant. We'll say that here. There we go. As long as we're on Earth, that stuff is all going to be constant. Big G is always constant, right? That's everywhere in the universe. Mass is just mass of the Earth, and d would end up being the radius of the Earth. So again, this stuff right here is constant. If that stuff is constant, then you could say, well, we could simplify this equation a little bit. What we could say is, that stuff right there, we're going to give it a new name. We're going to call this thing little g. And go to the next bit. There we go. We call that thing little g. So little g is, once again, just this part right here. It's g, m1, and d, where, again, m1 is mass of the Earth, d is the radius of the Earth, g is gravitational field intensity, or gravitational field strength. You'll hear it called both of those things. So this stuff right here. That's meters per second squared. I don't know why on this tablet it messes up my units, but that's meters per second squared. And just a reminder again, big G, still this 6.67 times 10 to the minus 11. That's the gravitational constant of the universe. You remember that from last day? Everywhere. And just note that this new equation, so this thing right here, little g being gm1 over d squared, this can be used for any body in space, so any planet, so we could do this for the Earth or the Moon, or I mean, you could even do it for yourself, I suppose, but it wouldn't be very meaningful. But we could do this for any object in space. It doesn't have to be in space, but we could do this for any object anywhere. So just note that on Earth, little g is 9.8. We saw, I think yesterday we were looking at this and we said little g for the Moon would be a different value. It's 1.6 meters per second squared. And that's where that value comes from. So for Earth on 9.8 that we use on Earth, it comes from just subbing in Earth's mass and Earth's radius into this thing. Alright, so let's try to use this. Let's use Earth's data to find g, and again, we know what it is, it's 9.8, but let's try it out. If we know, let's say little g is g m1 over d squared. We know these values. Little g is what we're looking for. Big G, 6.67 times 10 to the minus 11. Mass of the Earth. Mass of the Earth is 5.98 times 10 to the 24. And radius of the Earth, we talked about that the other day as well. 10 to the 6. And then don't forget this thing. We've got to square it. We work that stuff all out in our calculator. We're going to get 9.8 meters per second squared. That is just our g value on Earth. We know that already, but that's where it comes from. If we wanted to do this somewhere else, if we wanted to look at the radius of the Moon, and again, I don't know why my exponents keep messing up, but this is 1.74 times 10 to the 6 up here. I don't know why that keeps doing funny things. I've made a mess. There we go. That's 10 to the power of 6. If the Moon's gravitational field strength is 1.62 newtons per kilogram, what's the Moon's mass? This is a funny unit, this newtons per kilogram. That is identical to meters per second squared. And you can ask me if that's something that you want to see why it is, but don't be thrown off by that unit. Meters per second squared is the same thing as newtons per kilogram. So let's go ahead and try this one out. A couple things that we know. We know the radius of the Moon. Remember, radius of the Moon is going to always end up going into d in our equation. 1.74 times 10 to the 6. The Moon's gravitational field strength, just a reminder about that. Gravitational field strength 1.62, and again, you've got your choice. You can say newtons per kilogram or meters per second squared. That's the same thing. We're going to go ahead, we're going to sub into our equation. Let's see, I haven't done too much changing of color today, so we should change some color here. We know our equation, G is equal to big G m over d squared. You can call that m1 if you want, mass of the Earth, or mass in this case of the Moon. Now in this case we're given little g, so this is 1.62. Big G, we always know that number. 6.67 times 10 to the minus 11, that's a 7 right there. We're going to multiply this thing by mass. That's what I don't know, so that's what we're going to look for. And then on the bottom here, we've got 1.74 times 10 to the 6. And again, don't forget to square that thing. We're going to rearrange this whole thing. So the 1.74 is going to come up to the other side, so I'm going to end up with something like this. 1.62 times 1.74, that's a 4 there, come on, there we go, times 10 to the 6, again that's squared. Then we're going to divide by 6.67 times 10 to the minus 11, and that's equal to mass. So what we have done here, we've taken this number up over here and we've taken this number down on that side. And if we solve this thing for mass, we can say mass 1, let's see, 7.4 times 10 to the 22 kilograms. There it is. That is the mass of the Moon. Okay, if we rewrite our force of gravity equation, excuse me, we know, again, what we said before, we said this thing right here is little g. Okay, so if I replace in this equation, Fg is just going to come down. This whole thing right here all goes into that, and then the leftover mass from over here, you could say that comes in over here. What we're doing is replacing the circled part with little g, and mass 2 is still just there as it was before. So here's a new equation we've got. We can say Fg is just equal to mg, so there we go, that thing right there. We can use this. The other day we calculated our weight, and just for fun you could do that again today. You could say Fg is mg. If you wanted to know your weight, if you know that your mass, let's choose an easy number like 70 kilograms. Little g now, we know on Earth it's 9.8. If we multiply those two things together, then we're going to get 686 newtons. So yesterday when we calculated our weight, we used the big, huge equation. Now we can just replace it with this, as long as we know what little g is. So just remember, I can only do this if I'm on Earth, because on Earth little g is 9.8. If I go to the Moon, I've got to replace that with some other value. If I'm on some other planet, I got to replace it with its own value. Anywhere, anytime we're on Earth though, which for us is always, little g is 9.8, we can always use that. Yeah, so this equation now, Fg, which is Fg equals g m1 m2 over d squared, becomes Fg equals just mg. We're just talking about our little g values. On the surface of the Earth, little g is actually not a constant. That's due to a few reasons. Just remember that little g, this thing right here, little g depends on mass of the Earth and d, which is the radius of the Earth. Mass of the Earth is a constant, but radius of the Earth isn't. And you might argue that within certain areas, if you're, I don't know, if you're standing over a mine that has a bunch of iron in it, then the mass, the local mass of the Earth, right underneath you, the mass might be a little bit different. So for a few different reasons, little g values change. So you can check here, page 73, for little g values for different locations on Earth. We'll always just use 9.8 in our calculations. There's also here on page 75 of your textbook there's a table of little g values in our solar system. So if you were to go to the moon or Mars or something like that, some other planet, you could find out what little g is, and then you could calculate what your weight would be on that planet. When we're in class, we're going to check out this Bob Beamon video. Bob Beamon was a long jumper in the Olympics from quite a long time ago, but kind of a cool little video, and we'll check it out and we'll see how little g affected his jump, or his ability to jump in the Olympics. Nice, we got one more example here. If we are on Mars, little g turns out to be 3.61 meters per second squared. How much would Mr. Gaglardi's 3.0 times 10 to the 3 kilogram space Porsche weigh on Earth or on Mars? Nice, so let's check out on Earth first. On Earth, here we know little g is 9.8 meters per second squared. We're going to ignore this 3.6 number. We're not going to use that until we get to Mars. We know the mass of the object that we're talking about, 3 times 10 to the 3 kilograms. What we're going to look for is Fg. Remember, that's its weight. So if anytime it says that something weighs this much, or how much does it weigh, that's what we're talking about. So to solve for Fg, we know Fg is mg. So mass, 3 times 10 to the 3. You can just say 3,000, that's the same thing. Little g is 9.8. We're going to multiply those two numbers together, and we're going to find it's 29,400 newtons. So that's how much my space Porsche weighs on Earth. And for significant digits, you may want to say that's approximately 2.9 times 10 to the 4 newtons, same thing. But that's good sig digs. If we want to do this on Mars, then it looks a little bit different. On Mars, we're going to use kind of all the same steps, but little g now is 3.61 meters per second squared, rather than 9.8. Mass is the same thing, 3 times 10 to the 3 kilograms. Again, we're looking for Fg. Same thing that we did before, Fg is mg. Again, that's 3,000, I'll write it this way this time. This is 3.61, so little g is 3.61 now instead of 9.8. We go ahead and calculate that, and we're getting, let's see, 10,830 newtons. And again, for significant digits, I suppose we would round this. We'd say 1.1 times 10 to the 4 newtons, something like that. So it weighs significantly less. It's about a third. Things weigh about a third on Mars as what they do on Earth. Nice, and last example, I promise. I think I've said that a few times now, but last example here. On the moon, a 10 kilogram object weighs 16.2 newtons. What is the gravitational field strength on the moon? And if the radius of the moon is 1.74, and this is times 10 to the 6, the exponent 6 there, what is the moon's mass? Okay, so here's what we know. Let's look at part A. We know the mass of our object, okay, that's 10 kilograms. We also know the weight of the object, and just keep in mind, anytime it says an object weighs something, they're telling us Fg. Whoops. This is not that. This is, let's see, 1.62. Back to my pen here, 1.62. Oh, it's not that either. It is 16.2. 16.2 newtons. And they're looking for what is the gravitational field strength. And just remember, gravitational field strength or gravitational field intensity, that's little g. That's what we're looking for. We know Fg is mg. That weight then, 16.2 newtons, is equal to the mass, 10 kilograms, times little g. And it's little g there that we're looking for. We can divide both sides by 10. 10's over here cancel, and we're going to get little g 1.62 newtons per kilogram, or meters per second squared. Again, same thing. So that one's fairly straightforward. If we want to find the radius of the moon, now there's no radius, obviously, in this equation right here, in this FG equals mg thing, but we do know that there's a radius in this equation. Little g is equal to g m1 over d squared, where this thing right here, this d value, this thing, is the radius of whatever planet or object we're talking about here. In our case, it's going to be the radius of the moon. So to find the radius of the moon, we're going to use this. We just finished solving for little g. Okay, so that's right here, 1.62 newtons per kilogram. Big G, 6.67 times 10 to the minus 11. We know that to be true. Mass of the Earth. Let's see, what is the moon's mass? So that's what we're looking for, right? Not radius, but mass. So there's m1. Radius of the Earth was given. That's 1.74 times 10 to the power of 6. And I keep saying this, but don't forget to square it. We rearrange just like we did, I think, in one of the other questions. And we're going to solve for this and find that the moon's mass is 7.4 times 10 to the 22 kilograms. And there's the mass of the moon.